Hi guys, so we're doing a proof today. So we've been given that A belongs to M n cross n in the field with distinct eigenvalues. In our case lambda 1, lambda 2 up until lambda n, and been given that the corresponding eigenspaces are E lambda 1, E lambda 2, E lambda 3 up until E lambda k, and these have bases b1, b2, b3 up until bk. We have to show that b, which is equal to, in our case, b1 union b2 union b3 union bk, is linearly independent, right? So we could assume, starting off the proof, we could probably assume that we define some of these bases ourselves, right? That'd be easier. So we can define b1 to be, let's say, x1 x2. We could define b2 to be, let's say, y1 y2 y3. You could define b3 to be z1. That's all, right? So what we have to show is that a linear combination of this union a linear combination of this union a linear combination of this is linearly independent. So we have, let's say, a1 x1 plus a2 x2 plus b1 y1 plus b2 y2 plus b3 y3 plus c1 z1 is equal to 0. That's what we have to show eventually. But now, how do we show this? We know initially that each of these bases have a specific eigenspace, right? We're aware of that. That's given to us. So we know that this entire thing, and this entire thing, right, they belong to their specific eigenspaces. So this belongs to E lambda 1, let's say. This belongs to E lambda 2, let's say. And this belongs to E lambda 3, let's say. Okay? And we know that vectors from different eigenspaces, when combined, they are linearly independent themselves, right? The only issue lies here with the proof when we say that, when we kind of assume the concept of eigenvectors. So if we say that, okay, we can assume like these are eigenvectors, right? All of them, this set, and this set. But the problem is eigenvectors themselves, if you have non-zero scalars in front of them and if you have zero outcome, they will be linearly dependent. But you can't have eigenvectors themselves to be linearly dependent, which are present in the eigenspaces. So the only vector present in the eigenspace, except for the eigenvectors themselves, are the zero vectors. So if we, let's say, we assume a vector p equals a1 x1 plus a2 x2, vector q equals b1 y1 plus b2 y2 plus b3 y3, and we have, let's say, vector r which equals c1 z1. We know that any non-zero constant for in front of p, q and r, if they are zero, this implies p, q and r themselves cannot be eigenvectors, because this would defeat the entire purpose of having eigenvectors as linearly independent quantities. So the only other vector again in the eigenspace except for the eigenvector is the zero vector. So we finally deduce that this vector and this vector and this vector, all of them have to be zero vectors, right? That's our final deduction, and therefore this would allow us to say that when this is true, let's say in our case we have a1 x1 plus a2 x2 equals 0, then a1 equals a2 equals 0 has to be true. Similarly, if we could say this for this, right? So we have c1 z1 equals 0 would imply c1 to be 0, right? So this itself, the basis it belongs to holds because it contains linearly independent vectors, right? Similarly for this, and therefore we have b1 union b2 union all the other bases which we have union bk, they themselves in their combination are linearly independent. And this completes our proof. Thank you.